Hello, welcome back to es346 Basic Thermodynamics. This is module 4.3 on specific heat capacity. The section in the textbook is also section 4.3. Here are the two learning objectives for this module. At the end of this module, you will know the relationship between specific heat capacity and energy, and you will be able to differentiate between specific heat capacities at constant pressure and at constant temperature. Alright, let's start off by looking at specific heat capacity. And we're going to look at a fairly simple system first. So over here I have a rigid tank, and in here I'm going to have some material, and we'll make some assumptions here. First of all, we're going to assume that this is an ideal gas for now. And because it is a rigid tank, if we do any interactions on it, there will be no boundary work because the volume is constant. So the boundary work will be equal to 0. Now I'm going to talk about some general observations that you would see. If we were to put some amount of heat in here, Q, and measure the temperature, so I'm going to put a thermometer inside the tank, I would find out that I have a change in temperature, some amount, delta T. Now if I was to put in twice as much heat, so I put in 2Q, I would find out that my delta T, I'd have actually 2 delta T. The change in temperature would have been double. And in fact, if I put in 4Q, I would have had 4 times the change in temperature. So therefore, it's fairly clear that Q, there's some relationship between Q and delta T. And in fact, they're linearly related. And so if I was to put Q over delta T, I would have some constant called C. And it's constant with the amount of heat that I go ahead and put in. Now, if I was to write the first law energy balance for this system, delta U is the energy in minus the energy out, which is equal to Q. Well, we just saw from up here that Q is equal to C delta T. So we have a way to find out what our change in internal energy is from our changes in temperature only with this constant C. And we often call this C sub V because we did this at constant volume. And we will write this as delta U is equal to, and normally the constant is in a per mass basis. So it will be M little c sub V delta T. So that's the heat capacity at constant volume. Now I want to look at a similar system, but we'll complicate it a little bit. So once again, we will assume that we have an ideal gas inside here. But now we're going to go ahead and let the system move. So the boundary work is not going to be equal to 0. Now qualitatively, again, if I was to put in some amount Q of energy, I would find out that I have a delta T of the system. If I put in twice as much heat, I would get twice as much change in temperature. These are just observations that I would make. So once again, clearly there's some relationship between Q and delta T for this system. And again, if I was to go ahead and measure Q over delta T for different amounts, I would find out I have a constant. However, this constant is different from the value I would have measured before, even if I had the same material, the same mass, same identity of the material. That constant I'm going to call C sub P. I'm going to do that because this occurred at constant pressure. Now, if I go back and look at my first law energy balance for this system, so notice that we've got boundary work that is leaving the system as this expands. So my first law energy balance would be delta U is equal to the energy in, which would be Q, minus the boundary work. Now, in this case, if it's constant pressure, that boundary work you can rewrite as this is going to be Q minus P V2 minus V1. And that's equal to delta U, or we could write this as U2 minus U1. Now recall that the enthalpy was defined as U plus PV. So I could go ahead and take this PV term and combine it with the U2 and take this P and V term and combine it with U1, and I would have H2 minus H1 is equal to Q, and that right there was equal to Cp delta T. So now I have my heat capacity at constant pressure. It's related to my changes in enthalpy. And once again, this is normally written on a per mass basis where delta H is M Cp delta T. So where do we get these values of heat capacity? And so here I'm looking at table A2 from the appendices. And this is A2A. And these are a bunch of values that are relevant at 300 degrees Kelvin. So here on the left we have various different types of material. And I'm looking over at this third and fourth column third column is C sub P, and the fourth column is C sub V. And we'll notice that they have quite a wide range of different values depending on the type of material. The units on CP are kilojoules, or an energy, over a mass and a change in temperature. Let's see. So that came from that equation that, for example, delta H is mCp delta T. And we also see CV has the same units. They're energy over mass over a change in temperature. CV values, as you see here, are less than CP. And the reason that they're less is that in this case over here, we were having to do the boundary work, which was an additional amount of energy that we had to add for Q. And we'll look at that a little bit more later. So let's go ahead and do an example here. I've got a piston cylinder with 6 kilograms of nitrogen, and it's heated. So I'll go ahead and put some heat in Q. And it expands from 250 kPa, so let's write those numbers down. Our first pressure, P1, is 250 kilopascals. And my initial volume, V1, is 2 cubic meters. And it expands to 100 degrees Celsius, so that's my final temperature. T2 is 100 degrees Celsius. And it happens at constant pressure, so my final pressure is the same as P1, which is 250 kilopascal. And the question asks for how much energy was added by heating, so it wants to know what Q is. We have a piston cylinder, so we have some boundary work occurring, and this is constant pressure boundary work. So we can go ahead and write down our first law energy balance for this. So delta U, change in energy, is equal to the energy that goes in, which is Q, minus that goes out, which is minus WB. And since this is a constant pressure boundary work, we can do this as Q minus the pressure of V2 minus V1. And recall, delta U we can relate to the heat capacity, so that is equal to M C sub V T2 minus V1. So now over here I have an equation where I can solve for Q, and what I need to know are my initial and final volume, my initial and final temperature. And I've got a couple of them. I have my initial volume and my final temperature, but I have to get my final volume and my initial temperature. So let's go ahead and get our final volume first. So V2, and nitrogen is an ideal gas, so I can go ahead and find my volume as mRT2 over P2, the ideal gas law. Put in my mass of 6 kilograms, the value of R for nitrogen, I can get that off table A1, and the value is 0.297. And the final temperature is 100 degrees Celsius, which is 373 Kelvin. We need to report that in absolute in the ideal gas law. And the final pressure of 250 kPa. And so that goes ahead. I calculate that as a final volume of 2.65 cubic meters. And the other one I'm going to need, I need my initial temperature. So I can again use the ideal gas law, but now at the initial condition. So T1 is going to be equal to P1 V1 over mR. So plug our numbers in here, 250 kilopascals. Our initial volume was 2 cubic meters. The mass of 6 kilograms. And my value of R, which is 0.297. And now I have what my initial temperature is, which was 280. And this is in Kelvin, because this is the ideal gas law, so we're using absolute temperatures. So now we're going to go back up here, and I'm going to solve for Q. And from this equation, I'm going to move my PV term over to the right-hand side. So I've got Q is equal to mCV T2 minus T1. And then it's going to be plus P V2 minus V1. And I've got all my terms, so I just need to plug them in there now. So let's do 6 and CV. Now I know my heat capacity at constant volume. That's off the table A2A. The value of CV is equal to 0.743 for nitrogen. And T2, the final temperature was 373 minus 280. And now I add my boundary work term of 250 kPa. Pressure was constant through there. V2 of 2.65 minus 2. And if I go ahead and do all that arithmetic there, I put my final value of Q. Oops, go back here. Q is 577 kilojoules. So that's how much heat was added to the system. Now, I want to look at this problem. We're going to do it a different way. So this is the exact same problem where, again, I'm adding heat Q. My conditions are the exact same. The problem is the exact same problem, doing boundary work, but we're going to solve it using a different equation. So recall the first law energy balance is that delta U is equal to Q minus W, which is Q minus P V2 minus V1. Now, H, the enthalpy, is U plus PV. So I can go ahead and move this term, the PV terms over there, and I have delta H is equal to Q, and delta H is MCP delta T. So what I can do is I don't have to calculate the work term. It's sort of contained inside the enthalpy here. So let's go ahead and calculate what that is. So we have a value of 6 for our mass. I look up CP off table A2A, and my value of CP is 1.04. And then my delta T of 373 minus 280. And if I do that arithmetic, I get 580 kilojoules, which is, that's pretty close to the 577 we got before. That's just a matter of round off error. So this is a much simpler equation. I didn't go through the process of calculating the boundary work. It was contained right here in that delta H term. And that's the key of using enthalpy, and why it's even defined in thermodynamics, is it makes solving problems much more simple. Okay, I want to go ahead and return to the specific heat definition. So I've got on the left here my constant volume tank, and on the right I have my constant volume piston cylinder. And for the system on the left, we said that Q was equal to simply delta U, which was MCV delta T. And from here, I can find out what my definition of CV is, and CV is actually equal to delta U over delta T, or on differential form, it is du dt. And in fact, that's the definition of C sub V. It's the differential change in internal energy with a differential change in temperature. Now, looking at the piston cylinder, we had Q is equal to, delta U is equal to Q minus WD. And at constant pressure, we can move the boundary work term into the internal energy, get delta H is equal to Q, which is equal to CP delta T. Or usually we write the M delta H is equal to M CP delta T if CP is on a per mass basis. And this comes down to what the definition of the heat capacity is of C sub P. C sub P is defined as dH dt. So these are important distinctions. The definition of CV is du dt, even if the system is not a constant volume. The definition of CP is dH dt, even if the system is not a constant pressure. In this next example, we'll see why that's important. Okay, so this is our final example for this module. We have a piston cylinder device. Again, it contains 6 kilograms of nitrogen, and it's heated. There's heat going in, and it expands, again, from an initial and final conditions, but it goes against a linear spring. So recall from our previous module, if we have a linear spring and we look at our PV behavior, so this is the pressure volume, this is 0.1, this might be 0.2, and that's a linear line there along that process. And let's go ahead and write down our conditions here. First we have P1 is 250 APA, V1 is 2 cubic meters, final pressure is 400, P2 is 400 kilopascals, and my final volume is 3 cubic meters, right? And if I look at, I don't have a constant pressure process, the pressure changes. I don't have a constant volume process because the volume changes, and so you might wonder, well, what do I use? I can't use CP or CV in this problem. Well, if we go and just write our energy balance, it'll become really clear what we want to use. So let's write our first law energy balance for this system. So we've got an expansion against a spring with boundary work. The change in internal energy U is what goes in, Q, minus what goes out, which is WB. And this is a constant pressure process, so this equals Oh, I'm sorry, it's not a constant pressure process because I've got this linear spring. So what this ends up being equals Q plus my spring term, which is 1/2 P2 plus P1 times V2 minus V1. And delta U is M CV delta T. So if I want to solve for Q, I use CV to substitute for the delta U term, and I put my work term in right there. So let's go ahead and put our numbers in there. We see we're going to need to find out what our two temperatures are. So there's T2 and T1. So I'll do that first. So T1 is equal to P1 V1 over MR for 250 and the volume of 2. The mass in this was 6. And my value of R for nitrogen is 0.297. So my initial temperature T1 is 280 Kelvin. We did the exact same thing for T2. And so just to kind of save space here, again, if I use that pressure and volume, this mass, and this value of R, I find that T2 is 673 Kelvin. So now I can go ahead and solve for Q. So Q is equal to the mass, M, C sub V, which is 0.743. My change in temperature, so 673 is the final, 280 is the initial. And then what I need to do is go ahead and move my boundary work term over there. And oh, I just realized this shouldn't be a plus there. That should be a minus, right? I wrote it correctly up on the top, but that should be a minus term right there. Because the boundary work is leaving. The spring is expanding, or it's expanding against the spring. So I want to subtract 1/2 and 250, the pressure terms, plus 400, and my change in volume, which is 3 minus 2. So let's go ahead and do that arithmetic, and that should be 2077, and there is 4 years. All right, so there was a problem where it wasn't constant pressure, wasn't constant volume, but by starting with the first law energy balance, go back here, starting with the first law energy balance, it was really clear. I had delta U, so I used CV into that equation.